I thought that's a nice title for today's lesson. Vectors, an introduction. All right. Some terminology first. A quantity that can be represented as magnitude only, we are going to call a scalar. So a scalar might be your height. A scalar might be how many times you can jump rope in a minute. That kind of thing. So something with a magnitude only is a scalar. A quantity with magnitude and direction we're going to call a vector. So examples of vectors. The most common one is force. When you're dealing with force, you're going to be dealing with vectors. You need to know the magnitude of the force and which direction it's pushing. Velocity, acceleration, all of those things are vectors. And more generally, anytime you're representing a multi-dimensional object, something in 2 dimensions, 3 dimensions, etc., where there's a concept of distance, you can use a vector. So, for example, there in one class that I took, we did problems in an infinite dimensional vector space, where each component of the vector was an infinite sequence. So magnitude and direction kind of don't really make sense. The magnitude makes sense, but direction doesn't really make sense. But it's a multi-variable quantity where we have a concept of distance, or length, or magnitude. All right, we usually represent them. Our book calls the representation a directed line segment. I usually think of it as an arrow. We call this point the initial point, and the terminal point is where it ends. And any vector with the same magnitude and direction, I'm going to say any vectors with the same magnitude and direction are equivalent. So it doesn't matter where they're located in the plane. If they have the same magnitude and the same direction, we call those vectors equivalent. And we would call this vector either vector v with a little arrow over the top, or we could use the points, or vector AB with the arrow over the top. In print, vectors are shown in bold. And they usually use a small letter, a small bold letter, to show a vector. If our initial point is at the origin, then we say the vector is in standard position. And if the terminal point is the point v1, v2, we write that the vector v equals, with angle brackets, v1 comma v2. We call v1 and v2 the components of the vector. v1 is the x component, and v2 is the y component. If we have more than two components, we x, y, z, or you could just say the first, second, third, fourth, nth component. And we call this form component form. And that's the form that we'll use mostly. All right, we good so far? This all should be more or less review. The zero vector. The zero vector is the vector with components 0, 0. And be careful, because the zero vector is not equal to the zero scalar. They're different things. One is a vector, one is a scalar. All right, operations. What we're going to start with is basic operations, adding and subtracting. If u is the vector in component form, u1, u2, and v is the vector v1, v2, and c is a scalar. To add vectors or subtract, u plus or minus v, we add or subtract the components. u1 plus or minus v1, comma, u2 plus or minus v2. Add or subtract vectors, we add or subtract the components. Scalar multiplication. C times u. We just multiply each component by the scalar. And what we get, it multiplies the magnitude by C. And negative u, is just, we can think of our scalar being -1, is negative u1, negative u2. And this is a vector in the opposite direction. From u. So the negative turns it around. We don't do much with vectors graphically, but I just want to remind you that graphically we add head to tail. So if I have two vectors like so, this is u, this is v, this vector would be u plus v. Yeah.
So magnitude is Notation-wise, is with the double bars.
Yeah, we'll talk about the magnitude in just a second. And then we subtract. Tail to tail. So if this is U and this is V, oops, I want to change the color there. That's V. This vector would be U minus V. And the way that I think about that to get the direction of the difference correct is U minus V. If we turn V around, turn it negative, then we start here, go here, and end here. If we turn V around, negative V, that would be our initial point, and that's our terminal point. Properties with sums and differences and scalar multiples are exactly like you would expect from properties of real numbers. You can group your vectors any way you like. So you have associativity, you have commutativity. You can move things around. So I'm not going to list all the properties. They're exactly what you would expect from the properties of real numbers. All right. The length or magnitude. The magnitude or length of a vector V. We write double bars around our vector, and it's just comes from the Pythagorean theorem. We find it using the Pythagorean theorem or the distance formula, v1 squared plus v2 squared. And if we had more components, we would just continue adding things in there. There are other ways to find the magnitudes of vectors. This is a particular way, and it makes sense because we're used to using the distance formula in the plane, but there are other ways to find the magnitudes of vectors. In the vector space that I was talking about, where each component was an infinite sequence, the magnitude was that each component of the vector converged. So that's another way that you can find the magnitude is does it converge? Then yes, you can call the magnitude something. If it doesn't converge, then the magnitude is unbounded. All right, we also call this the norm of the vector. So the process of finding the length or the magnitude of something is called finding the norm. And what I was just talking about is there are other ways to find the norm of quantities. For example, in one dimension, the norm is the absolute value. That's its distance from zero. And that's another way you can define the magnitude of a vector. You could just take the absolute value of the components and add them together. Normal is a different thing. If our magnitude is 1, we call V a unit vector. And unit vectors are going to be very important for what we do in Calc 3. If V is the segment, directed segment, from between 2 points, P1, P2 to Q1, Q2, we can say that v is the vector q1 minus p1, q2 minus p2, terminal minus initial, and the magnitude of v, the norm of v, is this quantity. This is a 1. q1 minus p1 squared plus q2 minus p2 squared. And this is the distance formula. This is the length. If we think of this vector as a little arrow like this, we're drawing a little right triangle. We're using the Pythagorean theorem to find the length of the hypotenuse. That's exactly what we're doing here. What's that?
That's just moving it into standard.
Right, this just moves it into standard position. If c is a scalar, the magnitude of CV is the absolute value of C times the magnitude of V. So C just multiplies the magnitude by the absolute value of whatever that scalar is. Now this is what in pre-calc we took. I think we spend 3 days talking about this stuff that we're going to talk about in one lesson. All right.
Let's have 3 days of this. That would be good.
The unit vector in the direction of V so if V does not have unit length, then a unit vector in the direction of V is V over the magnitude of V. We're just dividing out its magnitude. And you'll also see it written as 1 over the magnitude of V times V. It's the same thing. This process is called normalizing V. So if normalizing a vector means finding a vector with magnitude 1 in the same direction. Yeah.
So if we think of scalars as only a magnitude, we can think of unit vectors as only a direction.
Yeah, unit vectors are you can think of them as kind of pure direction. So quick example, and then we'll talk about our standard unit vectors. If we want a unit vector in the direction of V equals -2, 5. What this is asking us to do is find V over the magnitude of V. Or normalize V. So V over the magnitude of V is just going to be the vector -2, 5 divided by the square root of -2 squared plus 5 squared, which is 1 over the square root of 29 times -2, 5. This would be fine as the answer, or you could write it as negative the vector -2 over the square root of 29 comma 5 over the square root of 29. Or you could rationalize the denominators. So -2 times 29 over the square root of 29. I would leave it like this. And you can check the magnitude of this vector is going to be 1. All right, we good there? Okay. In science, you will see this notation a little more with your standard unit vectors. The mathematical notation is usually the bracket notation. And if you go further in math, you'll see vectors represented as matrices rather than in bracket notation. Our standard unit vectors, I hat is the vector 1, 0, and j hat is the vector 0, 1. We can write any vector v that's written in component form is v1 I hat plus v2 j hat. This is called a linear combination. Of the standard unit vectors. So these two notations are equivalent. And what I'll do in class is I'll kind of just alternate back and forth between the I hat, j hat notation and the component form notation, just so we're familiar with both. But the bracket notation is more standard scientific or mathematical notation. I hat, j hat is more common in science. All right, good so far. We can also describe vectors based on the angle that they make with the positive x-axis. So our old friend trigonometry comes into play with vectors. So if we put our vector in standard position, and we think of this angle as going counterclockwise from the positive x-axis. And this is vector v. We're making a little triangle here. The x component of this vector is going to be the magnitude of v times the cosine of theta. And the y component is going to be the magnitude of v times the sine of theta. So we would say v is the vector magnitude of v, comma, sine theta, sorry, cosine theta, sine theta. Sorry, I did it backwards. And we could also write that as the magnitude of v times cosine theta I hat plus sine theta j hat. So often it's going to be convenient to describe vectors as vectors that have their initial point at the origin, and you describe them by their magnitude and the direction that they make with positive x-axis. So you might describe a velocity that way. The speed is 25 miles an hour, and you make an angle of 25 degrees with the horizontal. So projectile motion, for example. That would be the vector that describes the velocity of whatever your projectile is. All right, questions there. Okay, especially when you're dealing with forces, we call adding vectors. Forces in science more, forces, wind, etc. Adding vectors is called finding the resultant. So if you're adding a bunch of forces together, it might the problem might say that this force is described by this vector, this force is described by this vector, this force is described by this vector, and these forces are all acting on something. Find the resultant force. It's asking you to add all the vectors together. All right. One last piece of information, I think, is all I need to do. Yeah. Okay. You may see problems that describe vectors based on their bearing. Different spelling for bearing straight. Bearing angles. You'll see them two ways. They're always measured from the north-south line. In surveying and sea navigation, you might see something like this. So I'm going to say sea navigation. For sea navigation, it also shows up for surveying. The bearing angle is always acute. And you'll see something like this, north 37 degrees west. And what this means, I usually think about this backwards. 37 degrees west of north. So this is SW. That would be that angle. 37 degrees west of north. So south 28 degrees east is 28 degrees south of 28 degrees east of south. That would be that angle. 28 degrees east of south. Air navigation. In air navigation, your bearing angle is measured from due north. So your bearing angle might be 232 degrees. Mm-hmm. So what that means is we're making a 232 degree angle, something like this. From due north. So you'd say the plane is traveling at 800 miles an hour at a bearing of 232 degrees. That's the direction it's describing. Yeah, clockwise from due north. Yeah, because yeah. All right, I want to do one last example, and then we'll be done for today. Our introduction to vectors. Next time we'll talk about three-dimensional vectors. Well, then we'll add some new operations. So here's this vector 3i hat minus 4j hat. We want to find the magnitude and direction. So when it asks for the direction, what is it asking for?
The angle from the.
An angle. The direction is an angle from the positive x-axis. All right. The magnitude of E is 5. Square root of 3 squared plus 4 squared. How are we going to find the angle? Tangent theta is y over x. So that is minus 4/3. And when I plug this in my calculator, this says theta is inverse tangent of negative 4/3. Your calculator says, okay, we restricted the domain of the tangent function to negative pi over 2 to pi over 2. So this angle is negative 53.13 degrees. Yeah, usually with vectors we measure in degrees. But how do we get this in standard position? We want our angle as a clockwise or counterclockwise angle from the positive x-axis. This is a clockwise angle from the positive x-axis. So in standard position, minus 53.13 to be in standard position. And whatever that comes out to be. All right, questions? Okay.
Sorry, just back to Scotland.
Until you get in the homework. Until you get in the homework and you're like, he's like, this isn't you. I'm sure they like recognize it. Yep.
Oops, 85 through 90.
85 through 90 or 85 and
85 through 90.
That needs to understand they think most of it.
Mhm.